morning, my dear students, and welcome to the world of electronics. Our lesson for today is a sequence of lesson 1 of module 1 under LX123, which is semiconductor devices. The lesson will start with the measurements of the different types of diodes here, as well as the identifications of the diode symptom and their probable causes, with the application of these test instruments, such as multimeters and oscilloscope. There are two types of multimeters here. These are the analog multimeter and the digital multimeter. The digital multimeter is advantageous to use when it comes to the accuracy of measurement. So let us prove. We have here a battery that provides DC voltages. So when you measure the voltage of this battery, we have to set the range selector switch to voltmeter. Then select whether it is AC or DC. If we press that one, that displays the AC. So since we are measuring the DC, we will depress this in such a way that it changes to DC. For the voltage output of this battery is DC. Okay? We have heard the negative side and the positive is over here. The reading now is 9.54 volts. 9.54 volts. Or, if you wish to measure the resistance of this resistor, we have to move the range selector switch to ohmmeter. Then, we can tell nga we are at ohmmeter because the unit indicated at top is mega ohms. Mega ohms. Remember, with this position, we can also measure the capacitance by pressing this selector here. Okay, that is V voltage, ohms, nanofarad, diba? So we need to say, with this position, it is designed to measure ohmmeter and capacitance. But since we will be measuring resistance, so we will set this one to mega ohms or kilo ohms. Okay? Remember that resistor is a non-polarized device. So we can connect the two test rods in either of the position. Okay? It reads here 0.998 kilo ohms, or in ohms that is 998 ohms. It is very obvious, class, that this digital multimeter really gives the most accurate reading, since the decimal value is given in hundreds and thousands. Okay? See? Okay, we have here. Again. That is also the problem of this digital multimeter, because it delays the register of the value. That is the main disadvantage. Okay, we have already here 0.998. See? It displays the decimal value not only in tens, hundreds, but in thousands. See how accurate is the reading? But when it comes to analog multimeter, we will set this one to DC voltmeter. Set it to 50 volts, voltmeter range, because the output voltage again here is DC. This is DC. Okay, again we have here the positive side and the negative side. That reads, okay, the pointer is positioned at this meter scale. Okay, we are using 50 volts here. Then the pointer deflects at this point. At that point. So it goes like this. We have here the divisions, major divisions and minor division. This is marked 100 and this is 90. Although There is no indicated 90 there, but we can analyze that this is 90 and this is also 95. Then the position of the pointer is somewhere here. So, we can count. There are still 4 minor divisions here. 96, 97, 98, 99, and 100. So, we are only up to estimation. That is why we cannot get the most accurate reading when we are using analog. No, when we are using analog. That is the main advantage of the digital compared to analog. However, the disadvantage of using digital sometimes, it delays the display of the value. Okay. However, analog multimeter prevails sometimes for some instances because it is very applicable when you are checking defective components and finding the electrodes of these semiconductor devices such as diode, transistor, Philippine transistors, diac, triac, quadrac. So when we are using digital, it is very confusing. So it is very easy and there is a quick response of this analog. Okay, let us try this one. For example, for this diode, okay, when you are looking the set it to times 10 ohms, okay, you have here. Okay, let us try another diode here. Okay, it deflects. We are at forward bias. But when it is reversed, it doesn't deflect. But the main purpose of using multimeter here, which is analog, is to immediately look for the two electrodes only, the anode and the cathode. So it really, analog multimeter is very useful when you are finding the electrodes of the semiconductor devices such as transistor for the base collector and emitter, or for the ECR, cathode, anode, and gate, no? But when it comes to digital, it is really very confusing. So that is why most of the electronic industry or electronic company, not only digital multimeter is being used, but also analog. Because analog multimeter is very useful for that instances. Okay. However, class, both multimeters will be used as we go along the series of electronic activities today. Okay. Last meeting, class, we were able to discuss, to demonstrate, and perform the behavior, the types, and the applications of diodes. We even had performed and assembled the 3 types of rectifier circuits, such as the half-wave rectifier that uses 1 diode, the full-wave rectifier sinter-tap type that uses 2 diodes, and the last one is the bridge type using 4 diodes. But for today's class, I will be presenting to you the 2 special type of full-wave rectifiers. These are the bridge rectifier, wherein 4 diodes are already encapsulated here, and the dual rectifier. Anyway, we will come to this later on. We will at first proceed to the measurement of the different types of diodes. Okay, we have here. Last time, you were reminded when you are looking for the electrodes of the diode, we have to use times 10 ohms and above. You may use times 100, times 1 key, times 10 key, rather than times 1. So it is not recommendable to use times 1 when you are checking semiconductor devices, such as diodes, bipolar junction transistors, field effect transistors, UGT, PUT, ECR, diac, triac, quadrac, and ICs. For these semiconductor devices are very sensitive to excessive amount of current. And remember that times 1 offers higher amount of current. No? Because actually, when you check this diode using times 1, For example, this one. Sorry. We have here. This one. Okay. When the pointer deflects, that manifests that the current from the battery inside is circulating around this diode. And remember that times 1 offers higher amount of current. And remember also that among the meters here, only ohmmeter is equipped with internal power supply, and that is the battery. Okay. When the pointer deflects, higher amount of current will circulate around the diode. And surely the diode will be affected. No? Will be affected. Especially the other, like for example, ICs, mga bipolar transistors, field effect transistors. These components are really sensitive to excessive amount of current. So, refrain from using times 1 for they may cause partial if not catastrophic failure to these semiconductor devices. Okay? Okay, let us now come to the measurement. At first, let us measure the normal measurement of this diode. The purpose of this is to locate the electrodes, the anode and the cathode. Focus on the forward bias. When the pointer deflects, that indicates that there is a current flow, and it is forward bias. This resistance spread is negative, and this is now the cathode. Remember, resistance spread is positive, negative for the ohmmeter because it is connected to the negative side of the battery. Okay, so this is the cathode, and we have here the anode. And when you reverse the polarity, there is no deflection. It is considered that the diode is open or it is at reverse direction. Okay? When it is deflecting, conductor, it allows the current forward biased. Okay? Now, how can we determine if the diode is defective? Okay, we have here. This is open because pointer doesn't deflect even at forward bias. No? We have here the cathode and the anode. The polarity now of the battery or the test rods is already in correct polarity, but still there is no deflection. So this diode is considered defective. It is open. Okay? How about this diode? Both direction is deflecting, meaning to say it is shorted. No? It is shorted. Okay, it is at 0 ohm. 0 ohm. No? Okay? Shorted, shorted. We could no longer use this one in an electronic circuitry. This is good. Okay, this is good. Then, this is bad. Open. Okay. How about this Zener diodes? The same with rectifier diodes. Zener diode may also damage. There are 3 kinds of troubles also. Leaky, open, short. No? Okay, we have here. We will use times 10 again. Do not use times 1. No? As it may cause damage to these semiconductor devices. Okay. We have here. Deflect. That is forward bias. This is forward bias. It deflects the pointer. Then there is also a black band. For this rectifier diode, there is a white band or gray band. That is now the cathode. Here, we have heard the black band. This is the cathode. And this is the anode. No? Okay. The pointer deflects. Forward bias for the Zener diode. When you reverse, so there is a deflection. If you are using times 10. How about times 10K? Highest range. So there is none. But for the other Zener diodes, for example, this one, let us try. Okay? using times 10 10 ohms, it deflects forward bias. When it is reversed, there is no deflection. But when you are using times 10K as the highest range of ohmmeter, there is deflection. So you might think it is defective or leaky because at the reverse direction there is deflection of pointer. No, that is normal for the Zener diode. Because remember, Zener diode is also made of silicon. And the biasing voltage is somewhere at 0.3 volts to 0.7 volts. For the rectifier diodes, the material is made of silicon also, but the biasing voltage is somewhere at 0.5 to 0.7 volts. Remember that Zener diode operates normally at reverse direction. No? At the reverse direction. The Zener voltage, we must always think of the balancing voltage or Zener voltage of this Zener diode. So, to prove, or you should, so that we can assure of the balancing voltage or Zener voltage, we have to refer it to the diode manual and look for the Zener diodes we have here. So, this is, we have here 1N5230, that is 4.7 volts. And this is 0.5 watt, 1/2 watt. This is now the smallest power. We have another type of diode, the Zener diode here, which is 1 watt, a little bit bigger. So, when the pointer deflects at the reverse direction using the highest range, that is normal for the Zener diode. Especially if the voltage is smaller. That was 4.7 volts. How about this one? Oh. Reverse bias, there is a little deflection. Meaning to say that the voltage here is much smaller. If this is 4.7, then this is 2.7 volts. No? The higher the deflection at the reverse direction, the higher the reverse breakdown voltage or the Zener voltage. But here, very high voltage, 27 volts. There is no more deflection of pointer at the reverse direction because the Zener voltage is higher, around 27 volts. We can see that one. For example, this is 0.5 watt or 1/2 watt, and this is 27 volts. 27 volts we have here, 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 here. So that is 1N 52, 54, 52, 54B, 27 volts. That voltage is the reverse breakdown voltage. But actually, at forward bias, the voltage that will be dropped during forward bias is 0.3 volts to 0.7 volts. But remember, Zener diode is always at the reverse direction when it is applied in a circuit. No? Okay. So, don't be surprised if there is a deflection during reverse direction because the voltage there is lower. Unlike this rectifier diode, we have here, okay, use times 10. The pointer deflects. It is forward bias. The voltage there is 0.5 to 0.7 volts, the biasing voltage. That is the barrier voltage or the biasing voltage at the forward bias. But when it is reversed, there is no deflection of pointer even you are using the highest range. We have here reverse bias because this is anode actually, which is reverse in polarity with the battery. So, walang deflection because the lowest peak inverse voltage for this rectifier diode is 50. 50. And the maximum is 1000 based from the rectifier diode manual here. No? So, there should be no deflection at the reverse direction for the rectifier diodes because there is no peak inverse voltage 50 or below 50. Okay? So only for the general diode. Do not be surprised if there is deflection at the reverse direction because most diodes reverse breakdown voltage is lower. We have 2.1, meron tayong 2.7 volts, meron tayong 5.1 volt, 12 volts, up to 1,000 volts. Okay. There is no more deflection when your reverse breakdown voltage is 20 volts. So there will be no more deflection at the reverse direction for the general diode. But below that general voltage, there is deflection. Okay. How about for this? Again, before we left, let us review. We have to use times 10 ohms. That is the recommendable ohmmeter range when you are looking for the electrodes. Reverse bias, there is no deflection. Forward bias. Focus on the forward bias. So this is the cathode because this is negative for the ohmmeter. And this is positive for the ohmmeter and this is the anode. No? Anode, cathode. Okay? How about for this light emitting diodes? Light emitting diodes are designed to convert electrical energy into electromagnetic radiations at visible frequency or visible range or near infrared range or near infrared frequency. So, you can also test or check if light emitting diode is defective or not using times 10 ohms. Okay, like this for example. No deflection, reverse bias. Deflects. Then it lights. So we need to say the electrical energy or the current is circulating around the diode because it is forward biased. So that current is actually the electrical energy. It is then converted into electromagnetic radiation or light. Forward biased. Okay? So this should be the anode and this should be the cathode. No? Cathode because this is negative for the emitter and anode forward bias. Okay? You can notice class that the color of the light is different to each other. Okay, we have here green, whereas this one is red. Green, forward bias, anode again, cathode. How about this one? White. Then another blue. So different colors, different semiconductor materials being used. Semiconductor materials being used in manufacturing diodes are silicon, germanium, and gallium. For these rectifier diodes and zener diodes, the materials being used are silicon, of course, silicon. And we have also germanium. But for these light emitting diodes, the semiconductor material being used is gallium. For example, for this color, blue, there is actually a mixture, not only gallium. For example, blue color lead is manufactured using aluminum gallium arsenide. Aluminum gallium arsenide because there are lots of combinations of these elements in producing different colors of lead. Let us say gallium arsenide, gallium phosphide, gallium arsenide phosphide, indium gallium phosphide, aluminum gallium nitride, aluminum gallium arsenide. So, different combination of elements, different colors. Okay? Those are the semiconductor materials or materials being used in manufacturing light emitting diodes. in such a way that it can produce different colors. Okay? For rectifier diodes, of course, we have silicon and germanium. But for junior diodes, exclusively silicon only. No? But we have also light emitting diodes here. No? Walang deflection. Deflect. It is forward biased. This is now the anode, the black to spread. And this is now the cathode. But it doesn't light. There is no light. This light emitting diode actually is not defective. It is normal for this light emitting diode because this light emitting diode emits light at infrared range. It is beyond our visibility. It cannot be seen by our naked eye because this is infrared LED, infra. It produces light but it is beyond to our visibility. Cannot be detected by our eyes. No, cannot be detected by our eyes. Infrared LED. This is applied in mostly in remote control, for example. The application of this infrared LED is in our remote control, for example. We have here a remote control. When you press this, it gives light. And the light actually is detected by the infrared sensor of your appliance. For example, for the TV receiver, for the DVD player. No? The light is being detected by the infrared sensor. For example, this one. For the TV receiver, we have here the infrared sensor, or we call it infrared receiver. It is actually a combination of photodiode. It is actually a photodiode but combined with PLEP transistor as an amplifier. It has 3 terminals, but the actual photodiode is 2 only. Because the photodiode receives or sends the signal being transmitted by the remote control via infrared LED. After it is received by the photodiode, it is then amplified. It is then amplified by a transistor. No? That is for the infrared sensor. So that is why when you press any of the keyboard of this remote control, it gives light, but it is beyond our visibility. But this can be seen by means of video camera. Okay? Let us try. Alright? By means of video camera, you can see that there is flickering light with this infrared LED. It is an infrared transmitter used by the remote control. That is when you press. Every time that you press any of the keyboards, usually there is a blink. But if it is just like this, hindi natin makikita if it is blinking with our naked eye. That can be seen only by means of camera, no? Okay, because video camera is sensitive, no? It can see the infrared range, no? The infrared range of this one. By the way, the frequency that belongs to the infrared range is 300 gigahertz up to 4 terahertz. 4 terahertz. Because what is visible color, like blue, red, yellow, the visible range or the visible frequency are ranging from 4.7 terahertz up to 7.5 terahertz. Very high frequency. No? Okay. Okay, let us now come to the application of this special type of rectifier circuits. But before we proceed here, we happen to overlook this type of light emitting diode. A light emitting diode with 3 terminals. Meaning to say, it gives two colors. Okay, let us try. It gives light green. But on this side, red. On this side, green. So, the two cathodes are connected together. Anode, anode. Then the two cathodes. Because it goes like this. It goes like this. We have here. Okay. This is now the symbol of the light emitting diode. We have here a terminal. Terminal. Green, red. And this is the common. No? Actually, this type of light emitting diode is applied in a TV receiver, DVD players, that serves as a power indicator. No? During standby position, it is red. But as soon as the power keyboard, the power button of your remote control is pressed, like for example this one here, the power button of your remote control is pressed, the color changes to green, meaning to say it is already at on position or on condition. No? Standby condition or position. TV now is at turn on position every time that you press to on position of your remote control. No? Dual light emitting diode. Okay, let us now come to this full wave rectifier. We have here the dual rectifier. So it goes like this. Dual rectifier diode. Wherein two diodes are connected in inverse configuration. It is inverse because the two diodes actually are not connected in series. Because if it is in series, it goes like this. It goes like this, no? Okay, let us try. Okay, we have here. Let us first look for the two electrodes. Okay, we have here the cathode. This is now the cathode. And another here. This is now the cathode. Okay, let us connect them in series. Connect them in series. Okay. That is, two diodes are connected in series. Two diodes are connected in series. Diode 1. The cathode of this diode is connected to the anode of this diode. Okay. That is why this diode the two diodes are not connected in inverse connection. The two diodes are connected in series. No? In series. However, if the two diodes are connected in inverse connection, it goes like this. Cathode, cathode. The two cathodes are connected together, or it could be inverted, anode, anode. So there is no deflection at all. Both in different direction. No? Negative here, positive here, no deflection. Positive here, negative here, no deflection. So the connection is at inverse connection or inverse configuration. So the same also with this dual rectifier diode. No? Okay, when is it applied to a circuit? For example, we have here. No? By the way, Rectifier diodes are of different sizes and power. The bigger the physical size, the bigger the power. For example, or the bigger the current rate. For example, this diode is MBR 2500. It is 10 amperes, 400 volts. 10 amperes, 400 volts. The 400 volts there is the peak inverse voltage, no, of the two diodes. Whereas this one, this is a little bit smaller, no? This is probably, if this is 10 amperes, this is 5 amperes. Dual rectifier diode. Okay. Yeah, here, let us first perform a circuit. Dual. Okay. There are 3 terminals of this transformer because a full wave rectifier center tap type. The center tap type meaning the secondary winding of the transformer has 3 terminals. 12, 0, 12. So, when you are using dual rectifier, you have to use a transformer which is center tap type. Okay, let us connect here. Then the other one is connected here. Okay, here. The third terminal or the center terminal is connected to this metal case. For the metal case, actually, the metal case is the center tap. See, let us prove. If there is continuity, center terminal to this metal case, there is deflection, meaning to say they are connected together. They are connected, oh. See? Only for this terminal. That is why you can use this metal case as a connector for the center tap, or you can use another electronic breadboard connector. Pwede ka dito. Okay. You may use the center tap terminal. Okay, just like that. You can use this one here instead of using this one. Remember that this electronic board connector is connected to the center terminal. Okay. Okay, let us only use this metal case. Okay. We are now connecting. Then, let us connect also. This is center tap. Okay. The diagram looks like this. Looks like this. This is the AC source, the male plug. Then we have here the center tap, the secondary winding. We have here 12, 12, 0. The two diodes are here. Then the center is over here. No? Okay, it goes like this. The two diodes actually are encapsulated in this housing. No? So there are only 3 terminals at the outer side. So the 2 anodes now are connected to the 12, 12 terminals of the secondary winding, whereas the center tap, the center terminal here, is connected to the resistor going to this terminal here. And this should be the output line. Positive line, negative line. Okay? So, meaning to say, this is connected to the center. Hindi dito to. This is connected here. Center of this dual rectifier diode. Okay, wave here. Center. Okay. Then the other terminal is connected here. connected here. Okay, there is no capacitor yet, only the resistor. Then let us use this oscilloscope. The negative is somewhere here. Then the positive is somewhere here. Center tap. Let us check again. Negative over here. Positive is over here. Let us use another terminal. Okay. Okay, okay. Center tap. We have here. Okay. Half wave only. Here's the result. When we are using dual rectifier diode that serves as a full wave rectifier, we are using actually two diodes, no? Here, but being encapsulated into one. So, the output goes like this. It is full wave. And the frequency is, let us try to measure the frequency here. If it is doubled at the output, the frequency over here is 120 hertz. But the input is 60. So, full wave rectifier actually is also a frequency doubler. Frequency doubler. The AC volts is being converted into DC, pulsating DC, full wave. Because both half cycles, the positive half cycle and the negative half cycle are being passed. This is now at the secondary winding, but right at the output of the rectifier goes like this. Both positive half cycle and the negative half cycles are being passed at the output of the rectifier. If it is half wave, it goes like this. Let us remove one of the terminals here. It is half wave, meaning to say, although this is a dual rectifier, but we are disconnecting the one terminal. It is operating half wave, no? Then we can measure the frequency at the output. The frequency here is 60 hertz. The frequency is 60 hertz. We are disconnecting one of the terminals. It is 60 hertz, 59.9. No? I'm very sorry class for some technical problems. Okay? So, operating half wave, operating full wave. Operating full wave. operating half wave. That is operating half wave. The frequency is 6 Hz. This is operating full wave when two diodes are connected, but if only one diode is connected, half wave. Okay. That's all for full wave rectifier. Now let us come to the bridge type. We have here 5 types of rectifier, which is bridge. They differ in accordance to their sizes and appearance. This is square, much bigger, because the current rate of this is 35 amperes and the peak inverse voltage is 600 volts. 600 volts. This is actually applicable when you are converting AC voltage at the AC power line into a lower amount of voltage. No? Lower amount of voltage, because it is a power line. And usually the voltage there is almost 300 volts peak value for the AC power line. So this is very applicable because the peak inverse voltage is much higher. It is 600 volts. No? Okay. And the current rate is very big, 35 amperes. Then we have also a flat type here, also bridge. There are, meaning to say, this bridge is composed of 4 diodes which are connected in closed loop configuration. No? It goes like this. Closed loop configuration. Okay, we have here the AC. We have here the positive, the negative. The two cathodes are connected together, that is the positive output line. And we have here the negative output line. No, the anode and the anode. But anode cathode, it is connected to the AC. Usually, this is connected to the secondary winding of your transformer. Because the secondary winding of your transformer serves as an AC supply. It supplies AC volts. It is fed to these rectifier diodes via this line. Kaya, that is why there is a mark here. There is a sign positive, then negative. Then there is AC. We have here negative. These are the two anodes. Then, positive, the two cathodes. Anode, cathode, no? Based from this symbol. But in an actual circuit, the symbol for bridge rectifier goes like this. Just like this. This is negative. This is positive. This is the AC line. That should be the symbol, the actual symbol of a bridge rectifier. No? Okay. Because the internal connection of this diode, which is in closed loop configuration, goes like this. If this is positive, we have here the coa, and we have here the terminals. There is a sign here, positive, AC, negative. So, the connection of the 4 diodes goes like this. This is now the cathode, anode. Just like that. The two cathodes are actually connected to the positive side. Then, the anode, we have here also, okay, goes like this. 4 diodes are connected like this inside this housing. No? That is why, let us try to assemble this one here. Okay, we have here Okay, we are now using the other type of full wave rectifier, which is bridge rectifier. This is dual rectifier, bridge rectifier, based from the 4 diodes which were connected in cross loop connection. Okay, we will now connect this one here. This should be the AC. AC here, then another AC here. AC, then AC. The center tap here is connected to positive. Okay. By the way, there's a difference between full wave rectifier, which is center tap type, for the dual rectifier. Because for the dual rectifier, we have to use the 3 terminals. But for the bridge type, we will only use 2 terminals. That is 12-0. No? Leaving this terminal not connected. Okay. That is for the bridge type. That is the 2 differences. Okay. We will now try if there is an output voltage here. Or the frequency. Okay, it goes like that. It's still full wave. The bridge type. Okay, let us measure the frequency again. Let us measure the frequency. Whether it is 60 Hz or 120 Hz. The frequency is doubled, 119.8 or 120 Hz. Because the frequency over here is 59.9 or 60 Hz. But at the output of the rectifier, it goes 120 Hz. Doubles the frequency. Okay. Which of these two rectifier circuits? Full wave center tap type or full wave bridge type? When it comes to efficiency, both of them are good. Excellent, no? Both of these two rectifier circuits are excellent. But when it comes to cost, so dual rectifier is a little bit costly or expensive because it uses 3 terminals. Whereas, for the bridge, it uses only 2 terminals. However, although bridge is a little bit expensive because it uses 4 diodes. No? Anyway, you can use either of these two because this type of rectifier circuits, full wave rectifier, are applied to any electronic equipment, electronic appliances. Okay, we have here an example of this. This one here. This is actually a dual rectifier. We can tell nga this is dual because there are symbols right at the bottom. No, there's symbol here. There are actually 2 diodes connected in inverse connection. We have here this one here, inverse connection. Also here we have here. This manifests that this is a dual rectifier. No? Okay. That is why we have here also this main board of the LED TV uses dual rectifier. Okay. We have also here in this battery charger of your cellular phone. This is actually a battery charger of your Android cellular phone. There is a so-called bridge rectifier. This one here, bridge rectifier. Okay. This is bridge rectifier. This one here is not a bridge rectifier, although it has 4 terminals, but this is IC. This one is not IC, it is just a bridge rectifier. This one is optocoupler included in this switch mode power supply. Cellular phone uses charger. A charger actually is an AC-DC power supply. Although it is equipped already with regulator because it goes like this glass. We have here a switch mode transformer, a regulator transistor, and an optocoupler. They perform together to provide an efficient output voltage without fluctuation, without variation. It is around 5 volts for your cellular phone battery. The battery there, when it is low bat already, it should be charged, and this serves as a charger. It is actually a power supply, a rectifier circuit. The AC voltage here, 220 volts, is rectified into DC by means of this bridge rectifier, smoothed out by this supply filter capacitor. Then the voltage is lowered down into 5 volts DC, and it is regulated, which is needed by your cellular phone battery. Okay? Another bridge rectifier is here. This one, the LED bulb. I think almost lightings in your homes use LED bulb. We have here bridge rectifier. This one is bridge rectifier. This one is IC. IC regulator rectifier, wherein the 220 volts from the outlet or from the socket is converted into DC, and it is lowered down in accordance to the requirements of this light emitting diode. These are now the light emitting diodes. It is a surface mount device, SMD, because the light emitting diodes are connected at the surface of the solder side of your PCB. We have actually the solder side. This is a surface mount IC because the IC is installed or connected at the solder side. We have here the component side. No, it goes like that. So that light emitting diode is a surface mount device, or we sometimes call this one as chip light emitting diode. When it is called chip, CHIP, meaning that diode is connected right at the surface of the solder side. There are lots of components here, included the resistors, capacitors. We also call this as chip resistor, chip capacitor, or surface mount device resistor, SMD. All of these are SMD devices because they are connected or installed right at the surface of the solder side. Okay. Just in case you wish to install a power indicator, use light emitting diodes as a power indicator or signal indicator. Okay. Light emitting diode with series resistor. Okay. There is a competition for this, how to get the resistance that is connected in series with the resistor or light emitting diode. Okay, we have here so let us connect the diode across the supply filter or the load resistor or load capacitor. Then the other terminal is here. Okay. So the light emitting diode now is producing light, indicating that there is power at the output. There is power at the output. I'm very sorry, class, for the inconvenience because of the technical problem here. Losing contact of our breadboard connector K. The light emitting diode, which is connected right at the output, serves as a power indicator. It is actually in series with this resistor. No? So, how do you choose a resistance of a resistor to be connected in series with the lighting diode? Because without resistor, the light emitting diode will blow or will be destroyed. Because it cannot withstand the voltage outputted by this capacitor. The voltage at this capacitor, I think it is, okay, let us measure. Using voltmeter here. Using voltmeter. Okay. The voltage across, let us disconnect first this LED. Let us try to measure the voltage across this capacitor. The voltage is 16.4. 16.4 volts. volts. The output voltage from this rectifier circuits right at across this capacitor. So we call it applied voltage to this light emitting diode. Why is it, class, that it becomes 16.4? Hence, the voltage at the secondary is only 12 volt something. Because capacitor will store voltage up to the peak value. Remember, the voltage, let us measure again the voltage across this transformer. It is AC. So let us change the polarity of the AC, the type of current AC. So the voltage here is 12.7 volts. 12.7 volts, that is the RMS. 12.7 volts here, positive. We have also 12.7 volts negative. It is only 70.7% of the peak value, which is 100%. What is measurable by your tester again is only the 70.7%. Okay. Also here, we have 100% here. So, what do you think is the peak value? Okay, let us compute. Peak value is equal to RMS times 1.414. 1.414 actually is a constant value. Okay, we have here 1.414 times 12.7, 28 to 9, 28 to 9. So we have 8 to 8 2. Then 4 1 4 1. 8 7 10 1 15. 1 12. 1. This is 17 point something. 17.2. The peak value. This is 17.2 volts. How come it becomes 16.4? Because each diode, anyway, there are two pairs. The first pair will conduct first before the another pair. When we say pair, there are two diodes conducting during the first half cycle. When the polarity changes at the secondary, another pair will conduct. Then the first pair that conducting a while ago will now be conducting anymore, will not conduct anymore. So, we need to say there are two diodes. The biasing voltage is 0.6 plus 0.6 is 1.2. So, the peak value now is 17.2 minus 1.2. The biasing voltages for the two diodes in series. That becomes 16 volts. That is why the voltage that we measured at the output of the capacitor is only 16 point something. Based from the computation, it is 17.2. because the two diodes are dropping voltages, which are 0.6 and 0.6, which is 1.2 volts. That became 16.4. Okay? Now, how do you compute for the resistance of the resistor? So, applied voltage is 16.4 volts. That is right across this capacitor, DC. Minus the light emitting voltage. The typical voltage that can be applied to a light emitting diode is ranging from 1.5 volts to 3.7 volts. These are the range of the voltages that can be applied to a light emitting diode during forward direction, no? 1.5 to 3.7 typically. And the amount of current should be 10 milliampere to 30 milliampere. So, how to get the resistance? Series resistance or resistance of the resistor is equal to applied voltage minus the voltage of the lead. Resistance is equal to applied voltage minus the voltage of the lead over the current rate. Lead current. Applying Ohm's law. R equals B over I. So, we have here. So, we will use 10 milliampere, which is equivalent to 0.02 ampere. 16.4, which is the voltage right at the output of your power supply or across this capacitor, minus 3.4 as the typical applied voltage to a diode. It ranges to 1.5 volts up to 3.7 volts over the current rate is ranging from 10 milliampere to 30 milliampere. So we choose 20 milliampere, the center one. So 16.4 minus 3.4 is 13. 13 volts over 0.02 amperes. 13 divided by 0.02. 12. So, this is 6, 12, 10, 5, 10, 0. Okay. 650 ohms. That is why I am using here 650 ohms in series. No? Series. We have here. Actually, I am using 620 because there is no available 650 ohms color codes of resistor. I am using here blue, red, brown. That is 620 ohms instead of 650. Okay. Let us try to connect this one again. Okay. And let us measure the voltage across. Use DC. Okay. We have here. How much would be the voltage across diode? It is 3.2 volts. And the voltage across this resistor? 10 volts. 16 volts at the across this capacitor, which is a supplier of this lead and resistor, is divided in accordance to their ratings. For example, this lighting diode is 3.2 plus 10. Okay, it goes like that. So the purpose of this resistor is to limit the current of this diode, light emitting diode. Because if they are directly connected, isi-short natin. Okay? Without using this resistor. Oh. It blows. The diode is damaged. Because I directly connect the voltage 16 volts right across the diode. No more. You cannot use anymore this diode. So without resistor, usually the light emitting diode will blow would be damaged because the required amount of voltage for this diode is only up to 3.7. But the voltage now applied to this diode is already 16 volts. So the diode could no longer control the intensity of the voltage. So it damages. No, that's the importance of connecting resistor in series in order that it limits the current or drop the voltage. Only 3 point something volts should be at across this light emitting diode. Okay. That's all for now. By next meeting, probably I will be sending video clips again discussing the LED TV, explaining the internal screen as well as the processes of the current of the signal flow across the mainboard, as well as this LED bulb will be discussed in the next video clip. Alright, if you have queries and suggestions, please do not hesitate to send me, because good suggestions and questions deserve responses. Thank you and so long, my dear students.